Good morning, Mile High Video. This is Adam Ross. I work at Comcast on the linear video packaging team, and today I'm going to be speaking to you about synchronizing geo-redundant origins. So some context for this talk. Again, we'll be mostly talking about linear IP video. This will mostly be from the packaging perspective, so I'm going to be making a number of assumptions about sort of our inputs. So on transcode, encode, and from the mezzanine streams. I will also speak to both Dash and HLS. And then something to keep in mind as we kind of go through this is that a lot of the details are sort of specific to your player and CDN implementations or configurations. So it's not necessarily a one-size-fits-all, and your results may vary. I think it's important as we start to dive into this to sort of take and lean on lessons that we've learned from similar problems. In this case, I kind of think that synchronizing geo-redundant databases starts to look relatively similar. And one of the key principles that has come out of that is in computer science in general, is the CAP theorem, that effectively states, given a network partition, that you can have two of the three things listed, which are consistency, availability, or partition tolerance. So as we kind of move through this, keep those in mind, that I think a lot of the same principles apply here as well. So what does a synchronized origin mean to me? It's effectively, for our purposes, whatever facilitates a player switching from one origin to the other without having any errors or needing to retune. So to follow along with this picture here, the green path is the live HTTP path. Player in zone A that's requesting content from origin A, say, there's a network partition, and now it needs to, via the CDN, reach out to origin B and start reading content from there, that it should be able to do that seamlessly without issue. An example architecture of what this might look like, just generically, is, we have mezzanine feeds going into each of our compute sites that are then feeding into encode, transcode, packaging. There's some methodology of synchronization between the two, such that our CDNs and our players downstream can then switch seamlessly, as I've spoken to previously. Some of the upstream assumptions are for our source, for our mezzanine feed. We have either one source feed that's split, so essentially it's the same video and audio clocks between the two sites, effectively meaning that each site has the same input, or there's two source feeds that are normalized at encode or transcode. So we might have varying audio and video clocks coming in, but via transcode or encode, again, that site A is communicating with site B, and they're producing clock-aligned segments into the packager. What does this actually mean, right? So for segments, given that we're working with transcoders that are outputting puzzle-aligned segments, that you should be able to deterministically, given some piece of metadata in the file, name your segments such that if it's available in origin A, it should be available in origin B, given the exact same file name. Manifests are a little bit harder. There's a lot more metadata to keep track of, and this sort of looked like to me short-term metadata versus long-term metadata. The short term is stuff that is inside your current time shift buffer depth, so things like your current set of segments and otherwise, and that sort of over time gets baked into your long-term metadata. So what segments you have and what segments you don't have affects what your start numbers are, right? So we need to be able to reconcile both of these pieces. What does this look like a little bit more specifically? So for Dash and TS, for example, that we need some of the same period properties, the same adaptation set content at large, so the same representations, and then roughly the same segment timelines, such that start number maps to the same content. For HLS, it looks pretty similar. You want the same variant playlists, and then you want your sequence numbers to be meaningful and contiguous between both sites. So the first methodology that we sort of came up with was cooperative packaging. So effectively, both sites are publishing segment metadata between each other, such that when the packager actually needs to make the decision about what segments to include in the manifest, it has the complete picture, and it can make deterministically the same decision between the two sites. This offers redundancy in the way of, if a content gets lost in the network somewhere from site A that, it can just reach over from site B and say, okay, you have this, I'm going to include it in my manifest. Allow the player to redirect appropriately through the CDNs such that the content is pulled to both locations from the site that has it. To dig a little deeper, following with our same color scheme that we've been using for origin A versus origin B, say your local incoming segments are, suddenly stop coming, that you're in a network partition or something like that. You could potentially be seeing those segments from site B and fill those same representations or buckets that you're looking to fill to publish into your manifest. This in a manifest would look something like this, where, again, following our color scheme, you might have content from A or B interspersed throughout the manifest. Again, you can seed this through your CDNs, just having the player rely on HTTP codes and the failover logic there. Just for example, we have our packagers talking to each other, sending the segment metadata. The green path is our HTTP path, or our currently active path. Say we can't reach origin A anymore, that we should successfully be able to reach over to origin B and have the exact same set of content published there. For pros and cons, pros, this allows packagers to make more informed decisions, that you have all the information available in front of you when you're looking to decide what to include in the manifest. This is pretty resilient to data loss between other sites. Like if you miss a certain segment and then I have it, then just fill it in and allow the CDN to do its thing. And then another potential advantage is you could have your packagers choosing the segments based on quality. So if you have a lossy path somewhere in your network, or otherwise for MPEG-TS, for example, if you have higher continuity counter errors in one segment than the other, choose the one with fewer errors. Some of the cons, it's more complicated to implement, right? You need to have an HTTP API that is responsible for publishing and receiving these sort of messages between the sites. You potentially have a bunch of little messages going between the sites, which is not always ideal. And then, waiting on those messages to come in that you might introduce live point and latency, which is never ideal. The second methodology that we came up with, we dubbed minimal synchronization. And this largely relies on determinism. So given the same input or output from the transcoder, that our packager should be able to make the same packaging decisions as well. We do have, to get in synchronization initially, and just to make sure that we're still synchronized, that each packager would be looking at the other site's manifest and making decisions off of that if our the relationship between the start numbers and the segments and the content is still the same as we expect it to be. What this sort of looks like, for example, is origin B here is requesting origin A's manifest and making sure that it is relatively synchronized with it. Again, following our diagrams from earlier, that the green line is the HTTP active path. So say the network partition happens, we can't reach it anymore, that this should facilitate the player then being able to reach over to the origin B manifest, which looks similar enough to get it where it's supposed to be. In actual implementation and messing with this ourselves, that our transcoders sort of snapped to each other. Either they are producing PES-aligned content or they're not. So the packager effectively looked very similar in that it was either in sync or not, and we were trying to maximize the amount of time that they were in sync, such that if there were a failover event and the player needed to look to the other origin, that the likelihood that they were aligned was trying to be maximized. So in summary, for the pros, it's relatively simple. You're doing some of the same manifest manipulations you are in normal packaging. It's a little bit quicker and easier to implement. Like you don't need to define a spec or an HTTP API to facilitate the communication. You're requesting manifests through the normal delivery path. And at least in my experience in the Comcast footprint, that I feel pretty comfortable relying on the determinism for most of our footprint. There's some problem children, and you may need to resynchronize more aggressively, but that's not the majority of the cases in my experience. Some of the cons, it's not as resilient to data loss as the other solution. Depending on your environment, I think making the assumption that your sources are consistent maybe not the best assumption to make. And then depending on how you implement the actual resync events themselves, that you may need to be careful about when you do the actual resynchronization. So this is pretty much the end of the talk here. Thanks for coming and listening to me. Thanks for coming to Mile High Video, and have a good day with the rest of the talks.